All right, so like I said before, this has now been evaluated. We'll come back and take a look at it in a little bit. But we're going to start right here deriving the shape functions over the parent element. So we have 1 xc eta xc eta. All right. The A matrix is x xc minus 1. Again, we're starting in the lower left-hand corner and going counterclockwise. All right, so minus 1, minus 1. One minus 1, 1, 1, minus 1, 1. All right, and then I'm going to call these in ISO for the isoparametric shape functions, and they are x dot inverse A. All right, and there they are, and they're exactly what we have shown them to be before. Okay. So now let's define what we said x and y are using the mapping from the parent to the master element. I'm sorry, the parent to the child element, or the parent element to the arbitrary quadrilateral. So we use those shape functions to come up with that mapping. So we said xj, nj. Well, these are the nj. There's 4 of them. Okay. And then xj is, so essentially xj, nj, that's the definition of a dot product, right? So I can just take the 4 coordinates in the x direction and take the dot product with the nj, and then that's what I get for x. Okay. So the 4x coordinates, again, using the same number scheme. So the first one has x at 0, the second node has x at 5, the third node has x at 4, and the fourth node has x1, right? And then we're just going to take the dot product with an ISO. Okay, so that's what x is in terms of eta and xc. We can do the same thing for y. So the first one has y at 0, minus 1, 5, 4. Okay, so there's our mapping. So now we can determine that Jacobian matrix. Okay, so the Jacobian matrix is the derivative of x with respect to xc, the derivative of x with respect to eta, 0, the derivative of y with respect to xc, the derivative of y with respect to eta, 0, 0, 0, 1. All right, so that's the Jacobian matrix, and then the Jacobian J is what? Okay, so that's that. All right, we also need gamma, which is what? So now we have that. Then we can find our new B matrix. Okay, so our new B matrix is gamma times I'm wondering, it's actually times the old B matrix, but maybe I don't want to confuse you guys, so I'll just write it over. So it's gamma times table in ISO I D in ISO respect to C. So finally we're getting close, all right? So the integrand, right, that we want to integrate is B transpose C mat times B times J, okay? And that's all a function of xc and eta. So I'm just going to define a function xc eta that's equal to B transpose C mat B times J. And there it is. Ugly, but it's just all a function of xc and eta. All right? So now we're finally to we've transformed everything. Now we can integrate. So think about how long it took to integrate it exactly. Okay? And watch this. Now, the Gauss integration, if we use a single point Gauss integration, we have a weight function, and then we evaluate it at the point, right? So the weight function for a single point is 2, right? But we're going to integrate over an area, so then it's Wi times Wj, and you get 4. 2 times 2 is 4. And then you evaluate it at 0 and 0. So I know I'm talking a lot. It probably doesn't make sense, but just go back and look at those tables. Look at the formula for Gauss integration. So the numbers I'm going to plug in here are just straight out of those tables. Just plugging and chugging, right? I just happen to have them memorized for at least the first 2. All right. So the integral then, the K matrix, is literally 4 times F 0, 0. So you remember waiting for 3 minutes? Just like that. Now this isn't very good integration. Actually, I'm not even going to go back and show you. Compare this to the other one because it's pretty bad. Okay? Because remember what I said, the more non-rectangular the element is, the worse the integration is. Okay? So we're going to use a little bit higher Gauss integration. And when you go to 2 points now, if you remember, the weight function is 1. Right? So Wi, Wj is 1. 1 times 1, right? So here I'm going to have 1 times, and then I need to evaluate it at all of the Gauss integration points. So for 2-point Gauss integration, if you remember, it's square root of 1/3, square root 1/3. Okay, and we need to do it for all of them. So I'm basically writing out the summation, right? You could also code this up. You could write summation of whatever. So it's just easy enough to just for this, there's not that many, right? So we're going to go minus square root of 1/3, minus square root of 1/3, square root of 1/3, minus square root of 1/3, minus square root of 1/3, square root of 1/3, plus, plus. All right, and then we're going to not sure what it's telling me there. Let's see what this looks like. Okay. I don't know what I did before, but okay. All right, so there's our Gauss integration stiffness matrix. So let's go back and compare it to the exact solution. There's the exact one. So if I close these cells such that we can see them in the same screen, maybe. Okay. So there's the comparison. Exact to the Gauss integration. Now, you might think that's not that close. I mean, they're not exact, but if you look at them, the numbers aren't that far off, okay? And again, we do this because we're trading the accuracy for the speed, right? We could certainly, if we had a tool like Mathematica and you really, really wanted to, you could probably come up with a scheme to integrate every element exactly, and then you'd never be able to solve a problem because you'd never get a solution. It would take forever, right? So we're trading off, we're knowingly trading off accuracy for speed. Let's stop it.